essentially what I want to do in the next 10 minutes or so is give a very broad overview to this topic of the connection between solar system and exoplanet research. In doing so, I'll be giving a kind of flyby tour of some of my group's recent work. So hopefully in the same time, describe how it relates to the big picture goals of the center. And so I want to begin by acknowledging the contributions to this work, both from past collaborators and also from my current group members. And so you can approach a talk about solar system science in many different ways, but really I want to start with my overriding view of it, and that is that the way I see the current situation with planetary science is that we have the solar system where we have a wealth of data for a really quite small number of objects. And so a great example of this is some of the data we're getting back from the rovers on Mars currently. This is sedimentary rocks as viewed by the Curiosity rover. And honestly, despite this large amount of data, many of the remaining questions about the solar system objects are still wide open. And then we have a very, very different data set, which is exoplanets, and this consists of a large number of objects, thousands now, but for the vast majority of them, still very limited data. So this is one of these classic mass radius plots for some of the low-mass exoplanets which have been recently discovered. For some of these, we have a few additional constraints besides just mass and radius, but for most of them, that's really all we have. So there's a challenge involved in reconciling these very different sources of information. And one starting point you can take to build up a general picture is by doing in-depth case studies of individual solar system objects. And so besides Earth, I'm probably biased at this point, but I would argue that Mars is the most fascinating of all. And the reason for this is that Mars today is extremely dry and cold, but it was not in its distant past. And I could have picked from literally hundreds of images to demonstrate this point, but this beautiful picture of the Delta Jezero crater is as good as any other. This is a false color NASA image showing of course, the landing site of the Perseverance rover, which is currently operating on the surface. And so at a time when life was first emerging on Earth, we have a wealth of evidence for flowing liquid water on Mars. And what's really special about Mars is that it actually preserves this evidence, as Nick Tosca alluded to earlier, better than Earth does, because Mars after this point did, and likely before this point as well, did not have plate tectonics. So we have this record from billions of years ago preserved right on the surface. And this is a big and important climate problem because it turns out getting early Mars to the point where it would have been warm enough to have this water is very hard indeed. And so you can show this quite simply through an equilibrium temperature calculation. I'm not going to go through all the details of the terms here, but basically the sun, like all main sequence stars, its luminosity is evolving with time. And it would have been fainter in the period on Mars where we see all this evidence for water. And so if you do a back-of-the-envelope calculation, you get an estimate for Mars's equilibrium temperature of 210 Kelvin, or minus 63 Celsius, something you would kind of associate it with Antarctic winter on Earth, very much not conditions to give you liquid water. So there has to have been other warming mechanisms. And one of the ones that's been investigated extensively is the greenhouse effect from a thicker early atmosphere. There's different ways you can address this, but one powerful way is to use three-dimensional climate models. These are kind of similar to the models that we use for things like the IPCC report to understand Earth climate change, but in another sense very different because we really strip them down and put in physical processes from first principles that allow them to be more generalized. And so these models show that even actually with an enhanced greenhouse effect from CO2, you can't alone get to the point where you can warm early Mars. And so essentially what happens is you get enough CO2, it starts to just collapse out onto the surface as dry ice. But the models, importantly, do also show that when you have a thicker atmosphere, you start to get the regions where we see the majority of things like valley networks indicating past water acting as attractor regions for snow and ice. And so this has led to this idea that maybe Mars was in a mostly cold state most of the time, but with snow and ice returning to highland regions and then episodic melting causing the kind of evidence that we see. And so this emerging view, due to a number of groups now, is that early Mars was an episodically rather than permanently warmed planet, but also it likely had disequilibrium atmospheric chemistry. And so the reason for this, we think, is that you have loss of hydrogen to space over time, which is causing oxidation, but episodic supply of hydrogen and other reducing gases like methane from the subsurface. And so it turns out that those reducing gases cause quite effective warming in combination with CO2. So what this model is showing is, going through time, a fluctuating Martian climate where you get pulses of warming from reducing gases, leading to warming effects, although a climate most of the time which is much cooler than what you would need for a permanently warm and wet state. And without getting too lost in the details, we think that there are interesting correlations between this model and what we see from Martian geochemistry. And so for the sulfur cycle, for example, there's been recent observations of Martian meteorites that suggest that exactly these kind of fluctuations between reducing and oxidizing states may have been ongoing in this time. And so this is still kind of at a starting point. And I think some exciting work to think about for the future is, well, first of all, how these kind of predictions will compare with the evidence that we're currently collecting from the Perseverance rover, and also implications of this scenario for prebiotic Martian chemistry. Because if you have warm conditions and you have a reducing atmosphere, then that's exactly the kind of thing you need for formation of prebiotic molecules. And so I think exploring this using detailed atmospheric chemistry models further in the future is going to be very interesting. Shifting gears a little bit to early Earth rather than early Mars. And my group and many others in this area think a lot about how the basic processes of things like convection and precipitation would have varied. And this is a hard problem to investigate, because even for the present day Earth, we still have some troubles simulating these processes, but they're really important for understanding how climate would have evolved. And so, as one example of this kind of study, this is something that was simulations that was performed by my postdoc, Jake Seeley, that we're looking at a mesoscale model, which is something directly resolving cloud effects. And it's looking at conditions that are warmer or higher solar luminosity than present-day Earth. And really the main point from these simulations is that even when you go a little bit outside Earth's regime, the fundamental nature of precipitation changes, because you get new effects emerging from the interaction between radiation and clouds. And so there's a lot still to be discovered in terms of how these basic processes play out differently under different climate contexts. One of the things that in the future that I think is going to be important for thinking about paleoclimate scenarios, but also about exoplanets, is how these changes in climate that occur in different regimes are going to play out for planetary habitability. So things like carbonate silicate weathering effects, but also additional things like how it affects transport of H2O to the high atmosphere and loss of water to space over time. And so one of the useful things about thinking about water a lot in a solar system context is that it helps you start thinking about it with exoplanets. And then just to take one other example here, that this is work thinking about observability of water vapor on exoplanets. And it turns out for rocky planets, this is quite a hard problem, because studies have shown that for ocean-covered planets, even if there's water all across the surface, the amount of high clouds mean that in transit spectra, it may be quite hard to observe water vapor in the atmosphere with something like James Webb. But one of the things that we've been looking at recently is how this might play out differently on planets where there are more limited water inventories. And so it turns out, at least under certain circumstances, that you can have planets with a much smaller water inventory where the water vapor signal is more observable. And even kind of novel oasis-type states which can emerge due to changes in the circulation that are currently under exploration. And so I think all of this shows that you have to do theory in combination with observations to get the most detailed look at what kind of processes may be important when you're passing into the exoplanet realm. And so just a final thing to end on here is the attempts to look at surface liquid water. This is even harder to do than observing water in the atmosphere of an exoplanet, because you have to get through the atmosphere in order to do that. But one of the ways that you might be able to approach it is by understanding the way cycling of other elements, and so in this case, sulfur might couple to what the liquid water inventory is doing, because it turns out in the solar system, we have a planet like Venus where sulfur hazes are basically permanent in the atmosphere, whereas for Earth, when you have sulfur gases emitted from volcanism, they fairly rapidly get removed via rainout. And so it turns out if you do the detailed modeling on this using a coupled model with quite conservative assumptions, you can place pretty strong constraints on the water inventory, the liquid water inventory of an exoplanet using observations of SO2 gas alone. And these kind of explorations, I think, would need to be extended further in future if we're going to be able to make the most out of transit observations. So then, just to finish, this is final slide. I just want to make the point that if we think about the exoplanets that we're going to be able to characterize in the next decade with facilities like James Webb, they are in a new range of phase space compared to the planets that we are familiar with in the solar system. And so this is going to allow us to really probe basic questions about the way rocky planets behave that I think is going to be extremely exciting to do. And so besides the very first order things like presence or absence of an atmosphere, questions of great relevance to biology, like trends in atmospheric oxidation, is going to be of a lot of interest to focus on. All right, so I'm at 12 or 13 minutes. I think I want to end it there and leave up my conclusion slides and take any questions. Thank you.
Thanks for the talk. One of the things that I was interested in is how long do these transient hydrogen-rich periods last on Mars? What are the typical sorts of timescales for those?
Yeah, so in those particular simulations, the timescales are of order 100,000 years. And that is set from the diffusion limit on escape of H2 to above the homopause, essentially. So you need to get percent levels of hydrogen in order to get enough warming to get liquid water. And then to remove that over time, you're talking tens of thousands to a few 100,000 years, essentially.
And the partial pressure that you're showing is just of H2, or do you consider other reducing species there?
This particular model is very simple. It's just H2 or O2. But this is something we want to extend in future to have a more detailed representation of the atmospheric chemistry. Yeah.
I guess I was wondering, could you speculate, maybe, have there been any secular variations in the redox state of sulfur in the Martian surface and atmosphere? I noticed that you were talking about sulfates, but you also mentioned pyrite, and of course SO2 degassing from Martian volcanoes.
Yeah, it's an interesting picture. And so the big phenomenon I was alluding to here is the fact that in Noachian sediments, we don't see too much evidence of sulfate deposits, but as you get into the Hesperian, so Noachian is early in Martian time, and then Hesperian is a little bit later. In this later period where the liquid water is tailing off, we see a lot of evidence for sulfate deposits. And I think this is tied into what the groundwater is doing to some extent, because when it's wetter, you can flush sulfates deeper into the crust when they form. But also, I think it's tied to the redox picture, because if you have a reducing environment, then sulfate can be converted to pyrite on either short or long timescales, depending on what the temperature is doing. And so this particular plot here is of a paper last year. This is a team based in France that was interpreting the pyrite that formed as forming in situ due to alteration under a more reducing conditions. And so plausibly, this is evidence of a reducing atmosphere on early Mars.
If you were to put your money into improving the resolution of the models that you run, or the complexity of the processes, where would you go?
I got to say, I mean, so I kind of started off in this game as a GCM modeler, and I find myself getting less and less pro complexity with time, if that makes sense. I really think the key thing with models is to be as faithful to the data as possible. And the moment you start putting in model components that are not required by the data you have, it can be interesting to explore, but you are going into theory space then. And so for specific questions, there's specific answers. I mean, for the on the global climate scale, clouds are still the big one that we have major problems with, even for present day Earth. And so that's an obvious one that needs improvement. For these kind of evolutionary models where you're coupling together different aspects, being able to understand what the surface is doing, the geochemistry, volcanic outgassing, representations of the escape process in the upper atmosphere, all of those things fold into it. All of them are important, but for any given set of questions, you have to say which of these are critical and which of these can I neglect for now, because planets are complicated and rocky planets arguably are even more complicated than larger ones, and certainly in terms of their atmospheric composition.